Hi. In this project, we built and evaluated multiple regression models to predict medical insurance changes. Our objective was not only to compare performance metrics, but to rigorously diagnose model fit using cross-validation and learning curves. We first loaded the insurance dataset and inspected the structure. The target variable, charges, was highly risk-skewed. To stabilize variance and reduce the influence of extreme values, we applied a log transformation using np.log1p. This transformation improves numerical stability and often improves generalization for skewed regression targets. Categorical variables including sex, smoker, and the region were encoded using label encoder. We then separated features and target and defined a five-fold cross-validation strategy with shuffling and fixed random state to ensure reproducibility and reduce variance in performance estimation. We evaluated 6 models using cross-validation with negative mean square error, linear regression, rigid regression, decision tree, random forest, XGBoost, light GBM. Mean squared error was chosen as the metric because it penalized large errors more heavily and aligns with regression optimization objectives. From cross-validation result on the log transform target, decision tree had the highest validation MSE, indicating high variance. Linear and rigid showed moderate error, indicating higher bias. Random forest achieved the lowest cross-validation MSE. Therefore, random forest was selected as the best performing baseline regressor. However, strong performance alone does not guarantee proper model fit. To access variance control, we performed hyperparameter tuning using research CV with 5-fold cross-validation. And the best parameter turns out to be the max steps equals 8 mini sample split, equals 5 mini samples lift, and equal to max features equals SQRT. These parameters introduce regularization by limiting tree depths and enforcing minimum sample per split, thereby controlling model complexity and reducing variance. The best cross-validation MSE after tuning was approximately 0.144, indicating improved generalization compared to untuned configurations. To further diagnose model behavior, we generated a learning curve using the tuned random forest with 5-fold cross-validation. The learning curve plots training MSE and validation MSE as functions of training set size. A learning curve is a diagnostic tool that shows how model error evolves as more data is used for training. It allows us to distinguish between underfitting, overfitting, and well-balanced models. In an underfitting model, both training and validation errors remain high and close together. In an overfitting model, training error is very low, while validation error is significantly higher, creating a large persistent gap. In a well-fitting model, training and validation errors converge and stabilize with a small gap. For our learning curve, training error increases slightly as training size increases, which expected. Validation error decreases and stabilizes as more data is added. The gap between training and validation error narrows and remains small. This indicates that the model is not memorizing the training data, and that generalization performance stabilizes with increased data. And therefore, based on learning curve diagnostics, the tuned random forest is well fitted. Tree-based ensembles model outperform linear model here because the relations between feature and charges are nonlinear and include interactions. Linear regression requires manual feature engineering to capture these effects, while random forest model handle nonlinear splits automatically. Our evaluation process is approximate because we use the k-fold cross-validation to reduce the variance compared to multiple model families, applied systematic hyperparameter tuning, and grid search CV, and examined the learning curve to access model complexity, rather than relying only on aggregate metrics. To further test robustness, we use varimax/steps and generate learning curve for each setting to directly observe bias variance trade-offs. Next, cross-validation could also reduce selection bias. And learning curves are especially useful for ensembles, since strong average performance can hide overfitting. If validation error plat high while training error stays low, that would indicate high variance. If both error remain high, that would suggest high bias and the need for greater complexity or better features. In deployment, we would monitor validation error over time to detect disruption shift. If the database grows substantially, we could test deeper trees or gradient boosting, since more data can support greater complexity with lower variance risk. In conclusion, cross-validation selected random forest as the best model. Hyperparameter tuning controlled complexity and reduced variance, while learning curves confirmed convergence between training and validation error. Overall, the tuned random forest shows balanced bias variance performance, supported by both quantitative results and learning curve diagnostics. Thank you.